Okay, great. So we're going to calculate the domain of some function. So let's just start off with a few terms here. So some terminology. So let's talk about some terminology. GY. Okay. So the first one is a set of real numbers. Have you heard of that before? Big capital R. And we like to draw our R's when we do the real numbers with like a double bar, like that. And that indicates that that is a set of real numbers. So this is the set of real numbers. Set of real numbers. And that's to differentiate it from the set of imaginary numbers. We do not deal with the set of imaginary numbers in this class. It's actually called the set of complex numbers. And the set of complex numbers includes imaginary numbers and real numbers and any combination of those. We're going to stick with the set of real numbers. So those are pretty much all of the numbers that you can think of. So that includes numbers like 0. Okay, 0 is a real number. 1, 2 is a real number. 1.5, right? Some decimals. It includes all fractions. 3/7. Okay. It includes negative fractions too. So let's call it like maybe negative 18/19. Okay. It also includes irrational numbers, so numbers that you can't write as a fraction. And if you tried to write it as a decimal, there would be an infinite number of decimal places that do not repeat or have any kind of pattern, such as the square root of 2 and pi and e. So these are some numbers that I'm hoping we can become a little more familiar with throughout the semester. But in general, these are numbers that are, if you try to write them as a decimal, you would have a very bad time because they go on infinitely long and there's no pattern. Okay, so a number like you might know that like 1/3, for example, 1/3 also has an infinite number of decimal places, but there's a nice little pattern, right? It's 0.3333, or you could just even write it as 3 repeating, right? But a number like pi, there's no pattern, right? It's like the next number is completely it's not random, but it's impossible to determine based on previous numbers. So there's no really way of knowing it without actually calculating it directly. So the set of real numbers includes all of that, okay? And the set of real numbers, that's kind of what we're going to be, our main focus of this class is on. So in general, we're going to be looking at the set of real numbers. So when we look at our domain, so the domain of a function, is all values that we are allowed, and I'll sort of underline that, to input into our function. Okay? So it's all values that we are allowed to input into our function. So that might make you think, well, what does it mean to have something that's allowed, right? So allowed, let's just sort of clarify that. Okay. So what I mean by being allowed to input a number into our function, that means we are not breaking any rules of arithmetic. Okay, so some of these rules we've been learning about for a long time, right? Some of these rules we learned when we first started to add, subtract, multiply, and divide numbers. Okay, so for example, e.g., division by 0. That's bad. We cannot do any sort of dividing by 0. Okay, dividing by 0 does not make sense. It's not that we haven't figured it out, and it's not that it's just as simple as saying that it's infinity or something like that. It literally doesn't make sense. So if you were to try to introduce some value that if you divided a number by 0, you would get some kind of rational value, it would make the rest of arithmetic fall apart. So it's in order for arithmetic to work, division by 0 definitionally has to not work in order for everything else to work. Another one would be taking the square root of a negative. Okay, so in our real number system, which we're working with, so this set R, the set of real numbers doesn't allow us to take the square root of a negative. Now, I think it was around, gosh, I don't know when it was. A few hundred years ago, there was a mathematician who said, okay, you know what? I'm just going to say that the square root of -1 is equal to this value I. And I, as soon as you introduce I, then this is a complex number. A complex number, okay? And we are not dealing with the set of complex numbers. We're dealing with the set of real numbers, okay? So if we were dealing with a number that, or sorry, a function that dealt with complex numbers, then we'd be fine. You'd be able to take the square root of negative numbers. You'd have no issue at all. But because our functions deal with real numbers, there's no square roots of negative values. Okay, so those are the big ones. Another example that you might be interested in is 0 to the power of 0. That's something that does not exist. You might know that any number to the power of 0 is equal to 1, right? So 5 to the power of 0, that's equal to 1. But 0 to the power of any value is 0, right? So 0 to the power of 0, there's a direct contradiction. So this is undefined. Okay. So when we're looking for the domain of a function, we start off by looking at the set of real numbers, and we say, okay, which real numbers are going to be okay in the function, and which real numbers are going to give us some arithmetic errors. Okay, any of the numbers that give us some kind of error is not going to be in our domain. Okay, so for example, let's find the domain of f of x, and I'm going to define that f of x to be x squared. This is just a regular old parabola, right? This is the graph of a parabola. So this would be what we call a quadratic function. Okay, so here's our quadratic function. The graph of it is a parabola. Are we going to run into any kind of arithmetic errors if we square any numbers? Like, are there any numbers that we are not allowed to square? No, you can square any number you want, right? Negatives, you can square a negative number, you just get a positive value back, right? So in this case, so there are no numbers that you can't square. Okay, there's no numbers that you can't square. Therefore, the domain of f is R. So R being the set of real numbers. Okay. Another way you could express the domain, so you could also write, the interval from negative infinity to positive infinity. Okay, so that's another way of writing it. So that's just saying, okay, any number between negative infinity and positive infinity is fine. And we use these round brackets to indicate that we're not actually including positive and negative infinity. That's because positive and negative infinity, they're not actually numbers, right? I like to think of infinity as kind of like a direction, like east and west. Like you cannot You cannot like be in a position like your GPS coordinates will never be east, right? But you can move in that direction. You can walk in that direction. Infinity is kind of like that. So it's kind of like it's like a direction on either end of our real number line. So any number that you can think of is allowed here. So that's why we would write any number between negative infinity and positive infinity would work. Okay, so that would be the domain of x squared. There's no issues. You can square any number. What about this one? Let's try this one. Let me change colors here. Okay, how about so find the domain of g of x. I'm going to say that g of x is the square root of x. Okay, so there's my function. It's a square root of x. And now the very first thing that I see is this square root symbol. Okay, so we kind of just have to recognize some of these functions and some of the things that come up with these certain functions. So the first thing that I see is the square root, and I know I can't take the square root of a negative number. So that means that whatever I'm taking the square root of, in this case, x, must be positive. So the domain is, well, there's a few different ways of writing this. So so one thing that I know is that our values cannot be negative. Positive values are good. What about that number that's not positive and not negative? What number am I talking about? 0. Is 0 allowed? No? What's this? Can we take the square root of 0? Okay, let's remember what a square root is. So the square root of x is going to be some number y, where y squared is equal to x. Okay, is there a number that we can square to get 0? 0. Yeah, so in this case, 0 is okay. 0 is allowed. So I'm going to start off by writing this in interval notation. So I'm going to say, okay, 0 is the smallest number, and I'm going to use square brackets. The square brackets indicate that 0 is allowed. Okay? If I were to use round brackets, the round brackets would indicate that I can get as close as I want to 0, but I'm not allowed to include 0. So I could have 0.1, I could have 0.001, I could have 0.00001, but I could not have 0. In this case, 0 is allowed, so I use square brackets, and that's our minimum value. After that, as long as we have any number bigger than 0, that is a positive number, we're fine. So we'll have positive infinity. We follow that by round brackets, because like always, we can't include infinity because infinity is not actually a value. It's more like a direction. So that's one way of writing it. So this is what we call interval notation. And I'm assuming that we've done some interval notation in the past. We'll be doing lots of interval notation, so I'm not going to bother like teaching you all the ins and outs now. It's just going to come up as we go along. So this is what we call interval notation. And then another way of writing it is with set notation. So I'm going to write the same thing using set notation. Okay, so using set notation, I'm going to start off with a curly bracket. The curly bracket indicates that I'm talking about a set. So there's my set. Okay, the values that I'm talking about are x. So I'm gonna borrow that same variable, right? We're talking about which values of x are we talking about? Well, so let's say that our set is okay. Well, we have to start off with some other set. That's how sets work. Is that you start off with some set. So I'm gonna say that the first part of my set is x, and I'm talking about real numbers here, as opposed to complex numbers or integers or something like that. So I'm going to start off by saying x is a real number, okay? But not all real numbers work, right? So I have to clarify which real numbers I'm talking about. So I do that with a colon. Some people prefer to put a bar here like this, like a big straight line like so, okay? I prefer to have the colon. You can do whatever you like. So you can either do a colon or you can do a bar. They mean exactly the same thing. So I'm talking about real numbers, but not all real numbers. I need my real numbers to be greater than or equal to 0. Okay, greater than or equal to 0. And that's how we would write it using set notation. Set notation. So these colons here, what they mean is such that. Okay, so we're clarifying. Okay, so we start off, okay, yeah, we're talking about real numbers, not all real numbers, so it's all real numbers such that x is greater than or equal to 0. Okay, so that's how we would write that domain. Okay, another one that we should be aware of is let's do so find the domain of, let's call this one h of x. And let's say that that one is 1 over, how about 2 minus x? Okay, that's what we call a rational function, right? Okay, so the thing that I see here is division, right? Or a fraction, which tells me that anything in the denominator cannot be 0, right? We don't want to divide by 0. So dividing by 0 is bad. So what we say is, well, I mean, you can write it however you like, but kind of the way I think is that I know that if the denominator, which happens to be 2 minus x, is equal to 0, we have a problem. So we want to make sure that 2 minus x is not equal to 0. Okay, so I'm going to say 2 minus x is not equal to 0. And with an inequality like this, we pretty much do all the same things with a normal equation. So what I'll do is I will bring this x to the other side, like so, by adding x on both sides. So I'll do plus x. And what I get is that 2 is not allowed to be equal to x. Or in other words, x cannot be equal to 2. Okay, when x equals 2, we have a problem. And you can see right away, right? If we take a look at this, if x was equal to 2, then I'd have 1 over 2 minus 2. 2 minus 2 is 0, so I'd have 1 over 0, and that's not allowed. It doesn't make sense to talk about dividing by 0. So the domain, again, I'll start off with the interval notation. So the domain is, well, there's really no smallest number, so I'm going to start off with negative infinity. But then I go all the way to positive, or not positive, but I go all the way to, oh yeah, positive. I go all the way up to positive 2. But I'm not allowed to be equal to 2, right? I can go as close to 2 as I want, but I can't actually be at 2. So I close those sets of brackets. But then I want to carry on the other side of 2. So I join these with what we call a union, right? So this is what we call a union. It's important when you're making your union that, I know it's kind of silly, but I think a lot of people like to know about proper notation. We want to make sure that our U's look like this and not like this. Okay, so we don't put a tail on our U's. Okay, so it's just a capital U without a tail. Okay, and then on the other side of the union, well, we pick up where we left off, which was 2. And then we pick it, we don't have any maximum value, so we go all the way to positive infinity. Okay, so basically what this is saying is these are all the values less than 2, but not equal to 2. These ones are all the values greater than 2, but again, not equal to 2. So this is all the values, but we've just got one tiny little gap, which is at 2. So 2 is not included in this set. Okay, using set notation, let me just add in one more page here. So using set notation, we would have, well, again, I'm going to start off by talking about real numbers. So x is a real number. Okay. And the real numbers that I'm talking about are all the real numbers that are not equal to 2. So the only clarification that I need to have here is that x is not equal to 2. Okay. Any questions about that so far? No? Okay. Gonna do one more example. I'll try to make this one a little more complicated. Okay, so this one we might have to do a little bit of problem solving, but that's okay. That's why we're here in the first place. Okay, last example. Let's do. How about? Yeah, okay. I'm gonna do. I'll go back to F. So let's call. I should actually say state the domain. So state the domain of f of x. I'm going to call this one 1 over, how about 1 over x squared plus 7x plus 12. Ooh, spooky stuff. Okay, so we're going to state the domain of this one. Okay, this is going to be a multi-part question. We're going to have to break this one apart. But we're still going to follow the same steps of finding the domain of, well, in this case, a rational function. So this is a rational function because it's one thing divided by another thing. Okay? It's just that the denominator now is a little more complicated, isn't it? Right? This is a quadratic. Okay? So let's go ahead and see what we can do. So, recall that if the denominator, which happens to be x squared plus 7x plus 12, is 0, we have a problem. So the problem occurs, so we have a problem when x squared plus 7x plus 12 is equal to 0. Okay? That's what our problem is. So we need to figure out which values of x give us 0 in this equation. Right? So here's our new equation. We're making this equation based on the original function. So we're basically saying that, yeah, we have a problem when this is equal to 0. Okay, so let's figure out which values those are. Any thoughts of how we can do that? Yeah? Factor it, yeah. Any ideas for the factors? Yeah, x plus 3 and x plus 4. X plus 3 and x plus 4. Do you mind if I ask how you got those numbers? Factors of 12, yeah. So yeah, 3 times 4 is equal to 12, and exactly 3 plus 4 is equal to 7, right? So when you're factoring a quadratic, and this is the type of quadratic that doesn't have anything in front of the x squared, right? So we're kind of lucky here because we don't have a number in front of the x squared here. So all we're looking for is two numbers who multiply together to get 12 and who add together to get 7. And that's where the 3 and the 4 came from. So now we know that here, look at this. We've got one thing multiplied by another thing equals 0. Okay. And I do believe this came up on the review, the grade 11 curriculum review document. But in general, if we know that a times b is equal to 0, then a is equal to 0 or b is equal to 0. One of the two, right? Those are the only two possibilities. So this is going to give us two different solutions. 1, 2. So that would be, well, when x plus 3 equals 0 or x plus 4 equals 0. So the first equation, pretty straightforward. X is equal to negative 3, and here x is equal to negative 4. Okay? So those are the values that give us a problem. When x is equal to positive 3, or when x is equal to negative 4. Or sorry, I said positive 3. I meant to say when x is equal to negative 3 or x is equal to negative 4. So that's where our problems are, right? So let's write this in our domain. So what I'm gonna do, which sometimes helps my brain work a little bit, is I'll just sort of draw a real number line. So here's my real numbers. So I've got sort of, maybe I'll put the R up here. Okay, so I've got positive infinity in this direction. I've got negative infinity in this direction. I've got 0 somewhere around there. Okay, so the values that give me problems are -3 and -4. Oops, not -7, -4. Okay, so I'm not drawing it to scale. I'm not really worried about scale here, but it's just sort of helps my brain to sort of say, okay, so the domain, like the values that are okay, are all the values up to here, and then I have to hop over -4, and then I go all the way to -3, and then I hop over 3 and I go all the way to infinity. That kind of helps me remember when I'm writing the interval notation how to set it up in the right way. So I'm going to start off with negative infinity. And then I go all the way to -4. Don't include -4, so I use a round bracket. Give myself a union. And I pick up where I left off, which was at -4. -4. Then I go all the way to -3. And then I stop. I have to jump over 3, so I give myself a little union here. And then I go on the other side of -3. So -3. And then after that, I've got no more sort of gaps. So I can go all the way to positive infinity and then end it off. Okay, so that's using interval notation. And using set notation, I know that it's kind of silly that we're writing it in 2 ways, but you are expected to know how to use both of these notations. So I think that it's best if we just do as many of these in both ways as possible. That way, if you're asked, you can just stick to one. So using set notation, we'll just say x is a real number such that x cannot be equal to -4 and x cannot be equal to -3. And we close those brackets off, and we're done. Okay, any questions about that one? No? Okay. So some of these do get a little bit complicated, but as long as we just remember what the rules are, you may be expected to know some facts about quadratics. I might want to review a little bit of stuff on quadratics. That could be something that we do next week. But yeah, I'm gonna end the video here, and then we'll work on. Oh, actually, before I end the video, I just want to state what our homework is. So our homework is so on the last homework set, we went all the way up to question 3, including number 3. This time we're gonna do number 4, and then there's one more page after that that I will post, which is question 5, and just half of them, So that's what we're gonna be doing today. I'll end the video now, and we'll just spend the rest of the period